It's Thursday, the 6th of February. My name's Juan Brown. You're watching the Blanco Lirio channel, and it's time for an update on the 737 Runway Overrun Pegasus Flight 2193 in Istanbul, Turkey. Now reports are coming in that there were 3 fatalities and 179 folks sent to the hospital. We have some new information about this accident to share with you today. First, let's start with the weather radar loop put together by Simon Radecki of the Aviation Herald. And then we'll take a look at the grainy closed-circuit TV footage of the actual landing, courtesy of Voice of America. Then we're going to review the ATC audio tapes that Victor from VASAviation has put together, and he captures those from liveatc.net. I'll be providing links to all these videos in the description comment section below. Here's a quick overview of the entire flight and the thunderstorm as it developed over the arrival runway. We'll talk more about this in a second. Look to the far right of your screen for the long landing just touching down there. I think that's video anomalies why the aircraft appears to be porpoising. Then disappears off the end of the runway. This aircraft landed hot and long. That means they landed at too fast of a speed, too far down the runway, nearly 2/3 down the length of a 9,000 feet runway, with a tailwind condition and a wet, slippery runway. By the time they got to the end of the runway, the departure end of the runway, they departed the end of the runway at 63 knots, that's 72.5 miles an hour, or 116 kilometers per hour, and they went off a 66-foot embankment before finally coming to a rest after the fuselage broke up into 3 pieces. Trying to outrun a thunderstorm on landing is akin to trying to outrun a screaming locomotive at the railroad crossing track. The best thing to do is avoid the situation altogether using your superior judgment instead of trying to demonstrate your superior flying skills in landing in a thunderstorm. There's a lot of holes in the Swiss cheese model, as we say in the aviation industry, that are beginning to line up with this new data. Let's give that a review. One of the most critical pieces of evidence that's come to light is the ATC audio tapes provided, in this case, by Victor at VASAviation, who gets them from Live ATC. Take a listen to this.
Suntic 87 Romeo, wind 270 degrees, 22 knots, gusting 34 knots, runway 06, clear to land.
Clear to land, runway 06, Suntic 87 Romeo. Suntic 80 Papa, wait for taxi.
Suntic 80 Papa, right, so stand by please, runway will change, and latest wind 270 degrees, 25 knots. I will call you for taxi, stand by.
Stand by, Suntic 80 Papa.
The call sign of the incident aircraft, the Pegasus Flight 2193, is Sun Turk 87 Romeo. The tower clears Sun Turk 87 Romeo cleared to land, and of course gives the wind with that clearance to land as 270 at 22 knots, gusting to 34. This is worse than previously reported. If you do the tailwind headwind calculation on this, that's a 19-knot tailwind. Remember, the acceptable limit in the industry is generally 10 knots. It sometimes can be increased to 15 knots in certain cases, and with wet runways, it's generally considered a limit at 5 knots, depending on which carrier you work for. This is a 19-knot tailwind component, not counting the 34-knot gust factor. That also results in about 11 knots of crosswind. That's no factor. Then the controller announces that to the aircraft that's taxiing out to hold on to his taxi, we're going to turn the airport around. What does that mean? Well, it's not like the airport's a turntable. They're going to turn around. They're going to turn around the traffic flow at the airport and begin landing the other direction into the wind. That should be another big clue to this crew that something's going on. The controller also reports the wind as 270 at 25 knots, an increase in 3 knots from the previous report. Real quick, your ability to calculate these headwinds, tailwinds components, you don't have time when you're that close to landing to whip out your application, which we all have now. I'll explain more about that in a minute, and figure out exactly what the tailwind component is and if it exceeds the limits. But if you're landing on runway 060, or you're landing on runway 06, you are heading 060 degrees, and you can find the reciprocal heading real quick either by looking at the Jeppesen plate, looking at your vertical card compass if you have one anymore, or add 2 and subtract 2. Add 2 to 0, you get 2. Subtract 2 from 6, you get 4. So the reciprocal heading to 060 is 240. When she announces the winds are at 270 degrees, well, you know that's only, 30 degrees off from a pure tailwind wind direction. And when she mentions those gusts up to 34, and you're rocking and rolling in this airplane, that should certainly be enough warning to break off the approach, recalculate everything, and start over. The second big clue is going to be the stability of the approach. Let's back up and talk about the weather. As a thunderstorm approaches and passes by an airport, the thunderstorm is being moved by the winds aloft. In this case, it was being moved generally from the west to the east, or southwest to northeast. The winds on the ground, however, in a thunderstorm are considerably different. Generally, as a thunderstorm precipitates out, depending on what phase of the thunderstorm is in, how developed it is, the winds right underneath the thunderstorm, well, the precipitation falls straight out of the thundercloud, and it tends to disperse in a 360-degree pattern around the thunder cell. This can create very hazardous weather conditions, particularly for flying. Here in the States, we've got a lot of Doppler radar and other warning systems to help folks on the ground determine whether there's wind shear hazards on the ground. And this aircraft, too, is equipped with a lot of high technology wind shear alerting systems as well. But basically, if the thunderstorm is behind you and you're trying to land, you're generally going to experience tailwind conditions. If the thunderstorm moves, or if the situation moves that the thunderstorm is in front of you, you're generally going to experience headwind conditions. In this case, the thunderstorm was passing pretty much right overhead from the tailwind direction. This crew was experiencing an increasing tailwind situation, what you might even call an increasing tailwind shear. What does that effect have on the aircraft? That pushes you along. That pushes you along farther than you want to be, faster than you want to be. Faster because you're trying to maintain a steady 3 or 3.5 degree glide slope to the landing runway. As that wind pushes you along, it's effectively raising the steepness of that glide slope, so to speak. As that tailwind pushes you along, you are increasingly reducing power and lowering the nose to try to remain on that 3 degree or 3.5 degree glide slope without getting pushed above the glide slope. As you're coming back on the power and pushing the nose down, generally your airspeed is increasing. So that's what can easily produce what's known as a high and hot situation, too high and too hot for the landing situation. Remember, we want to land on the first third of the runway. This crew landed on the 2/3 of the way down the runway. Also, too, the next chain in the link. All approaches need to be stabilized by 1,000 feet. That means you need to be on speed with final configuration on glide path at 1,000 feet. At any time from that point on, you become unstable, off by more than 5 knots or less. Somebody needs to call a go-around. Generally accepted policy here in the States is it's a no-fault go-around policy. If anybody in the cockpit says go-around, even if you've got a third or fourth pilot in the back says go-around, you go around and you sort out the reason why later. Let's talk a little bit about the role of ATC, or air traffic control, in all this. Some folks outside of the aviation community, have some misconception about this. Remember, ATC is there to serve you, the pilot in command. It doesn't work the other way around. You, as the pilot in command, always have the final say. That's why you're paid the big bucks. That's why you got 4 stripes. You're the pilot in command. If you don't like what ATC is giving you, you need to negotiate or do something different, or go so far as to declare an emergency if you have to get into the conditions, the desirable conditions that you need to remain within limits. Usually here in the States, when a thunderstorm approaches a airport, they'll be watching, the ATC controllers will be watching it closely, and generally they will tend to close the airport down, and that'll eliminate the pilots having to use their superior judgment to avoid using their superior flying skills, and just shut the airport down and put everybody into holding patterns. And then pilots need to start working out their fuel remaining, and then start doing their diversions if needed, or waiting out the storm until conditions improve, upon which they can land. Regarding having enough fuel to go around, remember, every flight is flight planned to have enough fuel to go around, to divert, plus a proper amount of reserve fuel. So not going around due to fuel considerations is a very unlikely situation. Now let's talk a bit about the condition of the aircraft once it finally came to a rest. When you take something like a 737 or any similar sized airliner and chuck it off the end of a 66-foot cliff or drop off at 73 miles an hour, you've got a lot of energy that needs to be dissipated. And the best way to dissipate that energy is to break up the airframe, to break it up. Airframes are designed, well, they're not designed to be chucked off a cliff at 73 miles an hour, but they are designed to break up, to dissipate that energy. Specifically, the engines are designed with 3 mounting bolts. If there's a problem with the engine, a sudden seizure, that sort of thing, the engines will shear off of the wing before damaging the wing. By breaking that aircraft up, you are dispersing the physics, the energy of impact, because it's the sudden stoppage that is so fatal. The other thing is no fire. Aircraft are designed these days to reduce the possibility of fire upon impact or upon some sort of a crash like this. That means keeping the wing center section together, where the fuel is stored in the center fuselage tank and out in the wings with the wing tanks. The normal fueling, or the normal burning of fuel in these aircraft, is you burn the center fuel first, and the remaining amount of fuel at the end of the flight is left out in the wings. So if you can get the engines to break off, the hot engines to break off and away from the airframe, you can help reduce the chances of that airframe catching on fire. Now let's talk a little bit about airport design. As aviation is expanding all around the world, airports are expanding as well. Often these airports need to extend their runways using fill dirt. At the end of that fill is usually a rather precipitous drop-off. And a rather unfortunate design I see often overseas is these hard walls, security walls around the airport perimeter. We saw that with that recent Fokker crash, the aircraft impacting that wall. It's better to have a fence that you can break through rather than a hard concrete wall used as your security fence around the airport. Would an incident like this happen here in the States? Sure, that's happened before in the States. What comes to mind right away was just last May or so, the Jacksonville, Florida runway overrun with a Boeing 737. And chasing these thunderstorms, trying to outrun these thunderstorms, immediately comes to mind quite a few years ago, the American Airlines MD-80 in Little Rock, going off at the end of the runway there, resulting in fatalities, and the American Airlines 737 in Kingston, Jamaica. It was a result of the Jamaica incident, I believe, is when we came out with the mandatory runway landing distance calculation requirement for each landing on every flight. Remember, in previous videos we talk about the pre-flight video, the pre-flight huddle. Before we take off, we get together as a crew and we brief all the contingency conditions, or some of the more common contingency conditions, and what is our plan going to be for an emergency return, including dumping fuel or not, if you're in an aircraft that has that capability. Same thing on the landing. You brief every landing, approach and landing into every airport, and can brief some contingencies. part of that landing briefing is required now to include your landing distance required. Now, if you're landing at an airport that you land at frequently and the conditions are fine, you got lots of runway and it's dry conditions and the weather's good, if the parameters meet certain parameters, you do not need to get out the application, and physically calculate your landing distance. But if there's any change to the weather, if the runway is wet, if you're experiencing a tailwind, if you have a maintenance issue with the aircraft that may impact its ability to stop, for example, you've got a brake issue or an anti-skid issue, then you are required to do this landing assessment. And that gets the crew to thinking, especially in a situation like this, when you're landing in the bad weather, how close you are to the limits, to the tailwind limit for your landing. And in doing that calculation, a good crew will figure out exactly what is the maximum wind that the tower can give me that I can accept this landing legally. Whether it's legal versus smart is something the crew's going to have to decide. So I wanted to get some other updates out this week. I think we'll just cover it tomorrow, Friday, in kind of an open hangar session. We'll see you there.